Yeah, 1 second. I will share my. Yeah, my name is Bohdan. I'm from the University of Málaga, and I will represent our work about the dental reconstruction. Can you see my screen? Like everything is fine with the sound?
Yeah, we can see your screen.
Okay, perfect. Yeah. The title of the paper is the dental 3D reconstruction with some advanced key point detection, and I would like to represent this our team that is working on this topic, and why the 3D is important, is crucially important in the industry of the dental industry and for the teeth, and why it's important, and the application of this technology is very wide. Especially in the treatment of the patient for some for putting some implants, for some surgery, to plan the surgery, and so on. And for this purpose, the doctors, they need to have the device that will scan not only the dental structure, but also the face reconstruction to do the plan. But where is the problem with the current situation? Because the modern scanners, they quite big. They have some limitation, especially they are very expensive, and they need a lot of post processing, and they can guarantee the time nearly 0.5 millimeters, more or less. But also the process of scanning can be quite long and not applied to each kind of the patient. Especially there is scanners with some special LED system that can generate a lot of light noise. It can be probably not harmful, but it can limit the number of patients that can be used. And why scanning teeth structure, the dental structure, can be challenging. And because of these main four reasons, is first of all is the dental structure is very glossy and can create a lot of light artifacts because of the reflective coefficient of the teeth enamel is very close to the glass. So we are working with the surfaces not mirror but very close. And basically, if, for example, patient has several teeth together very close, the structure of the teeth is normally very same. There's almost white, and the shape is very same. So it's create a very challenging situation for the key point detection algorithm. And the same we have with the soft tissues, because they also don't have enough sharp details, color gradient, and so on. And to solve these problems and provide our idea with the simplest reconstruction only from the simple video that can be done by the smartphone or any HD camera or something like this, we need to discuss several ideas, several techniques that is used. First of all is Gaussian splatting, that now is very trending techniques that provide the opportunity to create a really high resolution 3D reconstruction. And basically how it works, after the key point detection and matching the key points, the algorithm creates some kind of blobs around each point. And what does it mean? It creates kind of color distribution around each point that was created after matching of the key points. So after structure from motion algorithm, we receive the sparse 3D structure, but we don't have it's sparse. And to fill these gaps, we should use this kind of distribution, and for each point create some kind of this color blob, and then the final result is just to summarize. So you can see here the ray going through several blobs and like do the summary, summarize all the colors together to do the representation. But the problem of Gaussian splatting is very nice for visual presentation, but for the industry, it's very important to have the structure of mesh. What is mesh is just is description of the surface. So each point should have like the triangles to create the surface around the object and the points. And to do this, one of the modern techniques is surface-aligned Gaussian splatting, or like with this short name sugar. And the basic idea is quite, it's very easy to understand. For each this kind of block, after the summarizing, we just need to recreate the mesh structure. So from each point, we start to generate a mesh structure, and so only by normalizing the depth coefficient and normal coefficient, we can do the same block but with the mesh. So basically, this is the idea. And what we did is we made for one patient, we create 3 kind of different scenario video with different lighting and with different zoom, but only for the dental structure, just to save the privacy of the patient and so on. And we did the full HD video with the 30 FPS more or less, and then we tried to follow this like ellipse path of the video capturing that is very typical for the industry. So the industrial scanners also use this kind of path to do the scanning. So we try to repeat everything, but only with the smartphone video. Then we do some subsampling of the video, extracting each like 5, 10, 15, 20, 25, and 30 frames to generate like high density or like sparse frame dataset. And then the question is which kind of detectors and key points matchers it's better to use. There is like 2 classic is ORB and SIFT algorithm. That is very classic and almost used in many scenarios. And how it works, basically the ORB is quite simple algorithm that detect key points only on the in the images that have a difference in the color. So for the simplest example, you can imagine the chessboard. So this algorithm is perfect for chessboard. So these corners with black and white changes will be detected perfectly. So you now understand that this dental structure is not good, and this scenario is not good for this method because the teeth, they don't have this kind of sharp edges. The next one is the SEFT. It's measure it creates some gradient histograms along the image and detect only the peaks of these histograms, just to understand where is the some kind of maximum of the small part of the image. So like basically we have a big image, we need to like create some kind of grid on this image and analyze each small like square, and then calculate where on this square there is some kind of peaks of the color, for example, or shape. So it's like basically the idea of ORB in how it works, but not detecting only the color changes, but also the changing in the gradient of the shape. But again, the method is very fast and it works good with the, now I will, later I will show the result that this method is more or less fine with the very dense frame, but when we go to some extreme position and of the capturing, it is not so good. And the last 3, these like methods that more advanced, they are based on some neural network structures. First is KeyNet. It's like one method, but it combines three kind of networks. It's KeyNet, AffNet, and HardNet, but they're working together because each particular network do like the different analysis. The first is KeyNet, is a network that just detect the texture on the image and set up the points where the image has any kind of texture. It can be changing of the color, of the shape, or anything. And then AffNet, they produce this affine transforming, basically do the orientation of the image, like from something on the corner to something like completely flat, to do this kind of analyzing. And this is very nice for cases when you're trying to scan something from different angles and like, for example, 360 or 180 degrees reconstruction, and give an opportunity to like align each frame one by one to each other. And the last one, HardNet, create some kind of fingerprint, some kind of descriptor for the final image. And for example, how you should to understand this method is some kind of analysis of the postage stamp that is was made a photo on some kind of perspective with some like angle, and by using this network you can align it and have like completely straight to the camera and extract all the parameters. The next is LoFTR, and this method is very unique because this method basically don't have any detector, so it works directly with the image. It just split the image into like thousands of small parts, and then like if we have two images, we're working with the two images, we split each image into thousands of small parts and then compare the pairs one by one, small parts. So imagine like two puzzles, and you put one piece and compare to others, and that's the basic idea. And the last one is like DISK plus LightGlue. They based on the it's some kind of the first. It's also a combination of two kind of networks. The first one, the DISK, they just again with the same simple with this algorithm, they detect the special points, and it's provide for analysis they use only the important points, not everything, and it's easier for matchers to detect the points, because it's not necessary to analyze every point on the, like for the previous method LoFTR, we just need to analyze like only the more important point. So it creates some kind of range of the importance of the points. And several words about each method have any like advantages, disadvantages, but we are working in very specific like dental scenario, and for this reason, as I commented, ORB is not working so nice theoretically, and in practice we have that result. That is not the application of this method for this kind of reconstruction is provide a very poor result. And the same with with the second methods, because especially with the region with the same structure is basically used because the algorithm have a lot of misdetection. There is enough points of the basic detection, but the matching is not so nice. And the next three methods that is more advanced, they provide a better results, all of them, but basically the third method, KeyNet, that combine three networks, works the best because of this affine transforming. They give an opportunity to rotate the image and work with the rotated image. And here is the example how it works with the one frame pair. You can see that the number of there is only 4 from 5 methods, because from this case, for example, ORB produce like can't detect nothing. They zero in layers in this case. So we have that you can see that the KeyNet have and this even this DISK plus LightGlue produce even more inliers, but the limitation for these methods is the computational cost and the time of calculation. So by the number of inliers, you have all 3 methods. Even in this case, these methods produce even more inliers that were expected in the dense scenario. But later, the decrease of the parameters is not so good, and especially in extreme scenario wherein when the angle from the T is like almost 19 degrees from the side, it starts losing points very much. And in this case, the method with the 3 networks is like a winner. And also, if you compare the like GPU cost for each calculation, like 3 network works also better. And here how we have the results, it's like basic pipeline results. There is like 3 main steps. The first one is the sparse points. That is the result of the only with the matching of the correspondence points after the key points detection. And then around each point, we should create this like Gaussian splat, and we create this like almost photorealistic 3D reconstruction. But the problem that is impossible to work with this in the dentistry, for example, to do some kind of alignment or all the things. So after this, you remember sugar reconstruction, we can create almost the same. So basically the quality is the same, but now it's a mesh. So it is possible to work and post-process this result in the special like software to align with any kind of data, for example, even for the printing or other things. And in this case, this is the best case reconstruction quality and parameters that from the dense capturing and very sparse capturing. And you see there is for dense capturing, almost all methods working fine and produce like these parameters is structure similarity. And when the structure similarity is higher than 0.9, it means that the quality is very high and like almost like photorealistic. But when it's low, we have some artifacts and all the things. And here is the presentation. So for example, I mean, this kind of artifacts, or here you have some kind of things, and like basically all methods gives them more or less like visually the same results. But very important to understand that for the dental industry, like each part of the millimeter is very important for the future like for the next analysis. So in this case, the three network combination produce the best results on all of the metrics and the speed and the computational cost. And here is the like for this patient, we have this intraoral scanning data. It's a very accurate reconstruction of the dental structure, nearly 25 microns. So, and if we make the comparison between our reconstruction from the I took the 3 network reconstruction, we can see there is a lot of blue region. That means like less than 0.25 millimeters, so it's 250 microns, so it's less than, so it's sub-millimeter range, and like other is almost green. So basically, more or less accuracy of the methods is less than 0.5 millimeters. Of course, there is some like region with the red structure, but like the arch of the upper jaw is more or less, it's fit perfectly. So for all sides, not only for the frontal, for all sides. And what is the main limitations of this work is really small sample data set, so for only one volunteer, and we tried to produce different kind of light scenario and with different view and different speed of capturing, and also the accuracy. So we have a good result with less than 1 millimeter, even like less than more or less 0.5 millimeter accuracy of the distance between, like, we can believe that this intraoral data scanning can be like a ground truth in this kind of measuring. And also of course there is a lot of light artifacts, but we are working in the like real scenario with the real like dental light that is now using in the dentistry like office. So of course this kind of capturing with some polarized light can be better, but yeah, the idea is to adapt the method with like to the real scenario. And but in conclusion, and I would like to say that the combination of three methods will provide the best output for this kind of reconstruction, of dental reconstruction based on only on the video that can be done by any camera or even smartphone camera. The entire pipeline to do the full reconstruction now takes like nearly 40-50 minutes. That in comparison with the industrial scanners that work nearly 20-30 minutes, it's more. But we should understand that there's a cost of this calculation, like of this device, is almost zero, because it can be done with any kind of video. And for our next step, of course, we would like to extend our data set to have more patients with different scenarios, with different light condition, if it's possible. And the most difficult part is to have this intraoral scanner data, because it's very specific data, and it can be done only in the with the guided by the dentists, to have the point like with the ground truth to understand if this method is fully suitable for the industrial application. Yeah, that's all. Thank you for your attention.